So, I will be talking about dispersion relation in CFT. So, we know that dispersion relation usually enables us to construct a function from the knowledge of its discontinuity, and I will discuss this today in the context of 4-point functions in conformal field theory, and we will exploit the analytic properties of the conformal field theory correlator and the operator product expansion, and we will see what we can gain from such a dispersion relation. So, I will begin with some basic CFTs which we probably all of you know, and then I will set up the dispersion relation. Next, I will discuss one of its applications, which is how to use this dispersion relation to construct correlator in Wilson-Fisher theory in 4 minus epsilon dimensions. And then I will summarize. So let us start with a brief introduction to CFT. So, we know that in a conformal field theory, the power of conformal symmetry lies in the fact that it completely fixes the 2-point function and 3-point functions. So, suppose we have two operators O at x and O at y, then the 2-point function is fixed, and this delta is the scaling dimension of this operator, and for 3-point functions at operators at I, j and k, this is also fixed up to a number which is the OP coefficient, the operator product expansion coefficient, and so the functional form is fixed from conformal symmetry, and we are interested in computing the operator dimensions and OP coefficient, which we call CFT data. And these operator dimensions are in turn related to the critical exponents of a theory at critical point. So, basically the problem of determining the critical exponents reduces to the problem of determining the scaling dimensions. And so, the thing is that if we know this scaling dimension and OP coefficient, we know everything about a CFT. Now, the question that I will ask today is it possible to define a CFT with the less number of data? And I will discuss this today in the context of perturbation theory, where we will see that it is possible in perturbative settings to define a CFT where we know these dimensions and only a few of these OP coefficients. So, basically we do not need to know all this data, and with this less number of data we can even constrain the CFT. So
the less data is all deltas and some C's.
Yes, yeah. So, schematically it means that if we take this input of the 2-point function, which is the input for the deltas, and use the dispersion relation then the output will be the 4-point function. Now these inputs we can take these inputs from Feynman diagram computations or from some other bootstrap computations. So what I will discuss today is, so although the 4-point function and the OP data, they contain the same amount of information. Basically, if we know the dimension and OP coefficient, we can sum all the information together and compute the 4-point function. But sometimes it's difficult to resum the data and get the 4-point function. So this dispersion relation bypasses the resum. So you feed this into the dispersion relation and you directly get the 4-point correlator, the summed 4-point correlator. So, and then from this 4-point correlator you can always extract the OP coefficient.
What do you mean by 2-point function?
I mean these are the inputs, dimension. Yeah.
So would one example of this philosophy be that in a large N field theory, if you know Cij case for single trace operators, you get the double trace guys free?
Yeah.
That will be like one example of this.
Yeah. Okay, so I'll consider the 4-point function of 4 scalar operators. For simplicity, we'll take 4 identical scalar operators inserted at points x1, x2, x3 and x4. And so this 4-point function is not fixed from conformal symmetry. It is it can be written in terms of a conformally invariant cross ratios u and v, or in terms of z and z bar. So I will just write the cross ratios. So I will frequently use z bar and u and v interchangeably. So with this, you can write the 4-point function. Okay, just. So this delta phi is the scaling dimension of the external operator. And this f, okay, I can just define this here. So this is how we decompose the 4-point function. So these are the OP coefficients squared, and these are the conformal blocks.
So this is like non-canonical choice of this design.
Yes, so I just introduced this factor for convenience, so we'll see why it's.
So the identity contribution will be U.
Yeah, I just included this u to the delta phi here, so it will be.
Oh, I
but
see, it's there.
yeah, it's there. Yeah, but it's just a matter of a choice. You can do it. Yeah. So this is the S channel expansion where we fuse together operator 1 and 2 and 3 and 4. Now we can use two properties of conformal symmetry. So one is that OP is associative. So it means that we could have as well fused together the operators 1 and 4 and 2 and 3 and end up getting this expression, and this is crossing symmetric, so these two expansion must give the same result. So it means that if oh sorry. So if OP is associative, it means that this is what we get. So this is the S channel, this is a T channel, and this is the U channel. And this we will use at some point. Now let us analyze the S channel conformal S channel correlator. So you can just use this expression. So this is a conformal block which is not, the closed form expression is not known in any dimension, but it's known in exactly in 4 dimensions, and there are recursion relations which allows us to compute it in other dimensions, and we will see that this this G and this is D dimension. So the D dimensional block it has 2 different factors. So it has a power law in terms of ZZ bar, and the rest we call G tilde. So one just let me write down the 4D blocks for simplicity, which is the product of this ZZ bar and some hypergeometric functions. And these K's are hypergeometric functions with some So here also you see that it has a power law and a hypergeometric function, and why I am writing it this way it will become clear in a moment. So
Small g, right?
this is the full G.
Small letter. No, in 4D there
No,
will be,
this is the complete 4-dimensional block.
but that's what you're calling with a small letter.
No. So this is G tilde.
This is a D-dimensional.
Ah, okay, yeah, sorry, yeah, sorry. Now, one can see like so this is known in terms of some power series expansion in Z and Z bar. One can see that this sum is convergent and this integral, this d-dimensional block is analytic when Z and Z bar lies in this regime. Now we will exploit analyticity in one variable, which is Z, and Z bar is kept fixed. So we will not tamper with Z bar and we will just use Z as our variable. So
2f1 doesn't have something wrong at x equal to 0?
no.
So if you take that factor out, the g0 to that particular power, then whatever is left has only branch cut starting from 1.
I will discuss it now, the branch cut structure.
That is
But 2f1 doesn't have any problem at x equals 0.
Defined as a Taylor series.
So yeah, I'll discuss it now. So okay, so the analytic structure of G so this is the Z plane, and this is 0, this is 1, and from the hypergeometric function, so if we have a hypergeometric function like this, then it has a branch cut starting from 1 to infinity.
So if you are drawing this, I should assume Z bar is in a nice range.
Z bar is between 0 and 1. Yeah.
Real? Or
Yes.
real?
Yeah. So this is the branch cut which comes from the hypergeometric function, and this is true also for the d-dimensional block. So this is the branch cut which comes from G tilde, and there is a power which sits in front, which is this, and it will have a branch cut when for Z less than 0 from generic non-integer powers of Z. So this comes from Z to this delta minus L over 2.
whole conformal block has this branch cuts that came from that 1 and 0 are the point where you are colliding. So these are the singular points, and then you have these branch cuts. Is there a way of understanding why this separated function has only branch cut in one direction?
What do you mean by one direction?
It has only branch cut starting from 1 to infinity.
No, it has branch cut also from 0 to,
This is the whole conformal block.
yes,
Whole conformal block has branch cuts from 0 to minus infinity and 1 to plus infinity.
yes,
This comes from the fact that if you hit this operator, at 1 and 2, then these are the two singular points and these are branch cuts. Is there an understanding why this new G tilde has only branch cut in one direction? G has branch cut on both directions.
By both direction you mean?
I mean, why does it have branch cut only from 1 to infinity?
That comes from this hypergeometric function, the structure of the function.
Right.
But that is not the full solution of the conformal block.
Yes.
That is not the full symmetry.
The OP is not arbitrarily singular. It is singular to little bit. And then once you get rid of that singularity, everything is nice.
The power of exchange of primary and power of exchange of descendants are integer related.
Should I proceed? Okay, so now I will use some property of the branch cut that originates from this power law, and will define the discontinuity of a function f z to be the value above and below the branch cut and the nice thing with this is that if we have some power law which is non-integer for any alpha, then the discontinuity is simple. It introduces a phase factor only.
For arbitrary dimensions, the statement about this branch cut structure is true even in other dimensions.
Yes.
And that you see from.
Okay, you have this d-dimensional block. So this is known. That is a power series expansion, but then you can do a sum and write it as an integral form, which is and the integrand is a hypergeometric function again. And then you can analyze the integrand, saying that okay, these are the structures, these are the specific values of z for which it will have a branch cut. Then you will see that it will have exactly the same branch cut.
So it is roughly like this shadow representation of conformal block, like 2 3-point functions, and the middle point is integrated, and from there you can see in arbitrary dimension?
No, it just comes from the definition of the block. Why do you?
Do you have an explicit expression in other dimensions? You don't.
Yeah, I have integral expression, but from sufficient to analyze the structure. From that you can see the branch cut structure. I don't have a closed form expression in any dimensions, but from that expression you can say that these are the branch cut structures, and that is not altered by changing the dimension.
Representation will also be integral representation. Okay, I see from here you see. Okay.
Physically, it's what you'd expect.
Because a block captures the contribution of an entire multiplet.
Yes.
Right? So the entire multiplet, what are the quantum numbers of the states of the entire multiplet? It's one delta, and then you just act with derivatives, right?
Yes.
That's all integer sheets. So if you just separate out the
Contribution
coming, the offset coming from the first guy,
then
everything would be
integer
integers.
separated.
And hence there is a Taylor series expansion. Hence, well, you could ask no analytic. Why is there no singularity somewhere else? But that's from physical, as you said. Yeah.
And with this you can see that the discontinuity of the correlator, I mean for each block which is this, so the discontinuity when z is less than 0 So this is what I will use.
And sorry, the nature of the singularity in your 1, is that like a logarithmic branch cut?
Yeah.
Well, sorry?
Yeah.
Log.
Yeah. So now these are the ingredients that we need, and we will set up the dispersion relation. So this is
Because it's just one block, it's not
Yeah, it's one. It's nice to have some of this.
yeah, this is for a single block, not for the full correlator.
I mean, the understanding of what kind of singularity to expect even in a single block at 1.
At 1.
Is there a
I will not exploit that because this is, so what I will be talking about, this is sufficient to extract information. But you can use crossing symmetry, right?
well,
So
you
from,
want to make a statement about the S channel block in the T limit, T channel limit. I mean, I don't know whether you want to, but I'm saying it would be nice to have some understanding of the singularity structure there.
I mean, mathematically,
okay, yeah.
it's coming from that integral representation of hypergeometric function. Like the hypergeometric function has the log 1 minus z near z equals 1.
What is this integral representation?
I can write,
Maybe we can talk later.
okay, yeah, I didn't write the explicit form, but yeah.
But for
So, but the point that I am trying to make use of is that if we have a power law behavior, then the discontinuity is simple. So, that's what will make life a bit simpler.
But in large and double trace operators in fast subleading or in 1 by n will get contribution from this discontinuity. Double trace operators in fast subleading or in 1 by n will get contribution.
It depends on the on this,
Yes,
at which order, yeah.
fast subleading or will have anomalous dimension.
Yeah, it could be.
So then
It depends on specific theory.
yes, in general.
Discontinuity.
Yes, this is the discontinuity it will contribute.
Yeah.
in general.
It could, yeah. I will show a few examples, not in large n, but in some, yeah. So the dispersion relation is like a mathematical relation. So where we use Cauchy's residue theorem, and we write the correlator like this as a residue of this pole . And
Slightly tangential question. Given the discontinuity,
yes,
what can one say about the analytic structure of the discontinuity? In this case, it's simple, but in general, is there a statement to be made? Can we
you mean going the other direction?
somewhere else? So discontinuity, the way one calculates, is defined on that cut.
Yes.
Can we analytically continue that inside, and what sort of structure should I expect?
I mean, you want to construct from the right hand side, you want to see what is the function. But
Discontinuity, yeah. Well, I guess that's part of what you will say, right? Okay, fine.
yeah. So this is the residue theorem. It says that if we so this is evaluated at the pole z prime equals z. So this is a point z. Now the analytic structure of the correlator follows from the analytic structure of conformal blocks, because it's the sum of the conformal blocks. So it will again have the same kind of branch cut. So this is 1, this is 0. And since the structure is the same, one can deform the contour . Okay. So this is how we deform the contour. Now you see that when we are deforming the contour, we have contributions from the arcs, and we need to take care of the large arc contributions. So this is basically the behavior when z goes to infinity, and in order to see that behavior, one needs to see the 1 over z expansion of the correlator, and this is this is G. So for each this is for large arc, and this goes as z bar 1 over z bar to the power something. So this the plus order 1 over z, order 1 over z bar. So these are all positive powers of 1 over z and 1 over z bar, and this has this power law dependence. Now see, because of this power we can say that only primaries with delta minus L, when delta minus L is negative or 0, can contribute to the arc at infinity. And since we are dealing with unitary theories in d greater than 2, which has this unitarity bound, so this is for scalars and this is for spinning operators, and you see that only delta equals 0 contributes to the arc at infinity. So it comes from this power. All the other powers are suppressed.
The left hand side should have been G delta Z bar, right? Why 1 over Z, 1 over Z bar?
Because
you want to estimate its behavior at infinity.
so this is the large arc behavior. So we need to decompose the correlator as a in powers of 1 over z and 1 over z bar.
Yes.
So this is like the U channel OP.
Yes.
So that will have this behavior, right?
Or is you're using the fact that U channel OPA.
Yes, yeah. Because that's what we need to analyze this 1 over z, 1 over z behavior.
Are you concluding something? Are you concluding that your 4-point function on the arcs is bounded by some power law, is it?
No, I am concluding that what are the operators that can contribute to the arc. So
apart from this spatial operator, most of them?
all these are suppressed. They will not contribute because all the other operators. So from this factor, only the operators having negative values of this delta minus L will contribute.
Sorry, in the U channel OP you have the prefactor Z bar to the power delta phi.
Yes, yeah, it includes the factor actually. I can just write down. Sorry. Okay, so f of z bar is z bar minus delta phi f of 1 over z bar. So this is a crossing equation, and what we do is we write this f of z bar like this: a g delta L and if we use this expression in here, then this factor will go away.
So is your manipulation happening at G or an F?
Where?
That's happening block by block.
Yes, yeah,
So-
because for each I am using the fact that for each values of delta and L, it's
So
not as a
in
correlator.
just one block you can go to the U channel like this?
Yeah, so this is the, like, no, this is not the level of the block. This is at the level of the correlator, and then for the correlator I am using this expression. So this is the crossing equation, and this is how I expand in blocks, and then
I see.
now I use this to
For examining what happens at infinity, you use the only.
yes, yeah, that's the only reason to get the large arc behavior.
Factors.
Yeah, just so.
So that's a negative power in the first line or positive power?
This is a negative power. That's the way we define this. We take this prefactor out so that
Yeah, and that should have been ZZ.
this is one over. So this is the S channel equals U channel,
Yes.
and this is the S channel expansion in terms of conformal blocks.
Okay.
And now
Oh, I see.
you use this, so this negative power will go away with the positive power.
But is it that your final conclusion is about the 4-point function, saying that on the arc this 4-point function behaves very nicely in some sense?
Yes, so this is all about the 4-point correlator.
But this arc is roughly like Reggie, right?
No, I am not using any Reggie behavior. I am not using any Reggie behavior. That is not needed.
There is no analytic continuation.
Well, this is analytically continued, but there is no Z bar is not being touched.
Yeah.
So your G and Z bars are considered separately, right? It is only Z plane, maybe one of the.
So the discontinuity is only in one variable. So this is, I will not exploit the other variable. So this is a single variable discontinuity.
Here Z and Z bars are considered independent variables,
Yes.
but in Euclidean domain it will be Z equal to Z bar.
This is not the
So
case.
therefore it is probing Lorentzian signature, and this arc at infinity, is it probing the Regge limit?
No, we don't need. So we don't need to analyze the Regge behavior. This is what we will be saying. This is sufficient.
What does it correspond to in terms of 4-point function? This is a very specific configuration. What configuration is it for?
This is not a specific configuration. This is for any general CFT.
Any general CFT, but you keep G bar fixed,
Yes.
and for G you are taking to which in some direction you are going to infinity.
Yes.
So this is like some very specific kinematical configuration in which you are saying certain things are bounded in a nice manner.
Yes.
What is this configuration? Can you?
It's not a Lorentzian configuration. It's some weird thing. It's an analytically continued thing. Z is real, Z bar is something. Sorry, Z bar is real, Z is something. Then it's Lorentzian only when both are real. Both are independent things.
Lorentzian and both of them are independent and
Yeah.
Some continuation of Euclidean thing, not like
okay,
So for Reggie, for example, you need to do this and come back.
correct, exactly.
how about I go along the real axis? Along the real so this is complex Z plane. In the x axis I go to infinity. So now let's keep G bar fixed and real. Now G is also real and going to infinity. So this is some Lorentzian configuration.
Reggie is you have to pass through the cut and then go to that.
Second sheet, you have to go to the second sheet.
and then go to that.
There is nothing happening like that.
This is just an infinity.
Yeah.
But I think maybe in the Well, remember the U channel maybe it has some weird interpretation.
So one thing is that when we are choosing the value Z bar between 0 and 1, it means basically there is so the Z bar cut lies between this. That's exactly the Z bar cut between 0 and 1. But one can actually show using some theorem, and there is a recent paper by Slava and collaborators. So they show that even on the cut, it converges in a distributional sense. So there is that point is not So it's something related to Vladimir's theorem,
You're
which
saying the U channel OP is not quite legal.
but in
There is a cut there.
yes, but using that theorem, one can argue that this is valid in a distributional sense. So
You could move Z bar a little bit away from the cut and then take the limit at the end, right? Everything you're doing here would work for every value of Z bar, or not? In some range.
but Z bar between 0 and 1 and real, that's what.
You can't make it a little bit complex?
That will change things a bit.
to change the
Yeah. So I am, maybe the final result will still be the same, but we didn't actually study that. But this is the simplest stuff that we can do. But one can rederive stuff using the shift in Z bar. So with this contribution, we end up getting this dispersion relation. So this delta equals 0, you can just plug it in there, and this contribution from the integral is 1. And we are left with two integrals between, so this minus infinity to plus infinity, and so this is from delta equals 0. So if we use this, okay, I can just, so it's the arc contribution. Yeah.
There is an arc contribution.
Yes. Yeah. So this is what we have, and so basically it means that one has to take care of the discontinuity which lies between minus infinity to plus infinity, and since we know that from the structure of the block it is basically minus infinity to 0 and 1 to infinity. So these are the two integrals that we are left with. Now at this level one can use crossing symmetry, and so what we saw that the discontinuity is simple when we are in this regime, when Z bar is less than 0. So let us see how this can be interpreted in terms of this. So this can be used, at this level one can use crossing symmetry and show that this discontinuity at Z bar greater than 1 can be written in terms of the discontinuity at Z bar less than 0, where, Z, yeah. And this is just the crossing symmetrized version. So we can compute this and just interchange this using crossing symmetry and end up getting this discontinuity. So what this means is, finally we have to do only one integral. And then we use crossing symmetry for the other integral. So this is the dispersion relation, and we have to compute this part only to extract information about the correlator. So now let's see how it works. So to start with, one can see how it works for mean field theory, where the 2-point function for the 4-point function is given as a contraction of is given as a weak contraction, and so here in this correlator we can use the conformal block expansion and just consider the S channel identity, which is delta equals 0 and L equals 0, and this FCZ bar will have this, and this discontinuity is again the phase factor, and Z bar is kept fixed. And if we do this integral, you end up getting, so now we plug it in here in the, in this expression, and this is what we get. This part comes from the crossing symmetry. So this is exactly the weak contracted correlator.
Sorry, what do I do with the weird 1 minus e to the 2 pi delta in the denominator?
Sorry, which one?
Yeah, that one, where your hand is just below that. Yeah. What do I do with the denominator?
This will cancel this.
Oh, there is that.
Yeah.
Sorry, I think so.
So after that, you from this expression you end up getting only this. So we see that only the S channel identity together with the crossing symmetry determines the full mean field theory correlator. So
Assuming the stuff is two double trace of it.
yes. So and one thing I would like to mention. So here, this what happens when delta phi is integer. So then this is 0, but then there is. So when this is integer, it means that it has poles at z equals 0. So, and use the fact that discontinuity of 1 over z is this is a delta function, and one can analyze the same thing and end up getting exactly the same result. So this is valid for all delta phi.
And you're using the fact that anything but identity exchange in mean field theory is double trace exchange, and that has zero discontinuity.
Yeah, yes.
How do you understand this discontinuity of 1 over z is equal to delta?
Okay. You can so since this is a distribution, you can think of it like if you have some test function fz and you integrate it from minus infinity to plus infinity, and then use, so what is this? Then you can just write the definition of this. So this is limit alpha goes to 0, z 1 by z plus I alpha minus z minus I alpha, and this is f of 0. And if we have higher powers, then you can act on with the derivatives, and this means basically you have say delta z some stuff. Here also you have delta z some.
Higher positive powers of course would be 0, right?
So it will also be, yeah. So it will be derivatives of higher derivatives of delta function. Yeah.
Z appear discontinuity of z to the n.
So what do we get from this? So we know that this is from the block expansion. You can write it, decompose it into blocks, where we have these operators. So these are the coefficients, say mean field theory. So these are the operators getting exchanged, and we can decompose this into this and then end up getting the values for OP coefficient for the mean field theory. So this is first computing the correlator, and then from decomposing it one can compute the OP coefficient. So this is for the mean field theory. Now let's see how it works for perturbation theory.
So that box thing is what you call the dispersion relationship.
Yes, yeah.
That's your final. Is that the thing that Caramo also has?
No, it's a single So there are things, so first thing is it's a discontinuity it's a single variable discontinuity, and Carreño has double discontinuity, which is different from this.
I mean, I'm talking about this more recent paper.
No, they have double discontinuity, and they have some kernel with that which they compute for anything.
They're not actually able to evaluate the final integral also.
Analytically, yeah. So they do some numerical integration. So
Even for mean field theory.
yes, yeah. So I'm not sure like whether one can get analytic stuff. So So computing correlators in perturbation theory. So we expand the CFT data in terms of any expansion parameter, say epsilon. This can be anything. So we expand the dimension, which is the bare dimension plus
Can I ask, what is the space of functions for which that box equation is valid?
Well,
if in 4-point function.
More generally, what is it?
As of now, it should be valid for any CFT, for any 4-point correlator.
But should I just think of it in terms of some analytic conditions that when a function has only this cut of this kind, and the branch point is of some power law kind,
And some follow property.
some follow property.
Yeah.
And symmetry between the two
Yeah.
branches.
Yes. Yeah. So, and we also expand the OP coefficient.
Well, you can then add
And this,
she had a discontinuity of 0 to minus infinity and 1 to infinity. She's written in terms of 1 because of that symmetry. You could just add the other part of the
No, but you could use a T-channel expansion, even if it is in terms of other operators. I'm saying it need not be symmetric.
No, it may not be symmetry.
Just you want conversion T-channel OP.
But you would need to know what the discontinuity was there. It won't be the same as this.
I think once you know all the branch cut structure of the function f z z bar, you can write this the discontinuity for this, and then two things that you need to take care of. One is the arc contribution. There, it could be that there are more operators contributing to the arc, and the other thing is that the crossing symmetry. And here the advantage is, so why am I using this? Because the branch cut structure, so the discontinuity when z is less than 0, it's simpler. It's easy to calculate the power law discontinuity than the hypergeometric function. So, yeah, in principle, one can.
I'm just wondering whether you really use the crossing symmetry or you just use convergence of T-channel OP.
No, use the crossing symmetry, because for other than using that, we would not be able to get the other part. So, actually, we are evaluating this discontinuity, but using the crossing symmetry. You could have as well used directly the expansion, the branch cut from that, but that is not simpler. So, we are actually using the crossing symmetry.
Well, you want to estimate what the value of f is
Yes.
near 1 to infinity slice. Right?
Yes.
But so in order to do that, I could simply use the T-channel expansion.
Yes.
Right?
Yeah.
Doesn't need it. I don't need it to be crossing symmetry.
But you won't know the answer for what the discontinuity is.
Yeah, I need two discontinuities.
Yes. Yeah. Yeah. If you know that, then it's fine.
Right.
She's just it's easier for her because
Yes.
evaluating one integral.
Yeah. Also, it's a little less data. specified data and one cut PP to specified data.
Yeah, so suppose, so here also you expand everything about mean field theory. Now the point is that if you use the fact that the discontinuity at z less than 0 has this phase factor and you plug it in these values, then then this part is proportional to the anomalous dimension of this. So this is the advantage of using this.
So you can use the free G.
Yes, yeah. So it means basically you have this So the first order, at first order, everything is determined only by this dimension. You don't need this. This doesn't appear here. So that's why it's a less number of data. And okay, so finally, this is probably, you can just do it at each order, and at each order you will see you need the dimension of that order and the OP coefficient of the previous order that you can like compute by decomposing the correlator. So I will now give an example of how to use this to construct the Wilson-Fisher correlator.
And the anomalous dimension of the external operator enters.
Yeah, it's there in this delta phi. It's how you define. I think it will become clear when I can just show an example.
So the identity of exchange will also change a little bit.
Yes. So let's see how it works for Wilson-Fisher theory. So we consider the 4 phi correlator in phi 4 theory in 4 minus epsilon dimension. So we always need the anomalous dimensions of all the operators as our input. That we cannot constrain using the dispersion relation. So we need this dimension, which we take from Feynman diagram or maybe from some other bootstrap computations. And so this is the spin 0 operator getting exchange, which is the phi squared. So and we also have spinning operators, double trace operators. And at this point we are using the fact that the phi phi OP contains identity and double trace operator at leading order, and all the other operators are suppressed in epsilon. So these are the inputs.
Free theory OP coefficients, I can think of them just as mean field theory OP coefficients at n equals 0, right?
Yes, yeah. Actually, yeah. n is some stuff n 0 plus higher order. So yeah, and this we can already compute from this. Just plug in the value for the delta.
The OP up to order epsilon or epsilon square? The correction is already
That we don't need at this order. I'm just
so you need to know up to order epsilon.
yes. So the point is, it depends on at which order of the correlator you are computing.
Yes.
So if you are computing order epsilon correlator, then you need the anomalous dimension of that order and OP coefficients of previous all the orders.
Right. So in the equation above, phi plus phi is identity plus.
These are the double trace operators.
Then the correction comes at order epsilon square.
Yes, epsilon.
But if you want to compute 3-point functions up to order epsilon square, then you need to know 3-point function up to order epsilon.
Epsilon square will come later, yeah. I'll just start saying epsilon, yeah. It depends on specific order which you are computing.
But A does get order epsilon correction, right? Maybe it will
It depends.
compute it next order. But
Yes, yeah. It gets order epsilon correction, yeah. That's true.
So the ANL is delta n 0 plus order epsilon.
No, this is plus order epsilon square, but it has this actually, yeah. It depends on delta phi, which will also receive correction at order epsilon.
Okay.
Because it comes from this, and this depends on delta phi.
Fine.
So it's like just a way of writing.
Fine.
Now, now if you look into this expression for phi square, you see that there is an anomalous dimension at epsilon, but for spinning operator, the anomalous dimension starts at epsilon square. So if we want to compute this F1 for Wilson-Fisher theory, then we just need this one anomalous dimension. So it's simple. So only phi square for F1, and the discontinuity is simple. So there is only one conformal block. So this is delta is 2 for phi square, and spin is 0. And from this we can, and these are all 4-dimensional blocks since we are at leading order.
The reason the delta was epsilon for 0 and epsilon square for phi square, just that your perturbation
Yes.
itself was
Exactly.
delta 0 square.
Exactly. For some other theory it could not be the case, then you have to take that into account. So this comes from this block. And
the block is so simple.
yes, so there is only one block, only one scalar block of dimension 2.
It's not some hypergeometric business. It just
It's hypergeometric, but it reduces to this because scalar, it's for delta equals 0, delta equals 2 and L equals 0. Yeah. So now you can use this discontinuity and plug it in the expression.
What about the correction due to identity exchange? This is due to the contribution of delta 0, right?
Yes.
And you had started with an identity exchange that came with delta phi.
That is, since I am perturbing mean field theory, everything is.
I see. And you assume the thing is.
Yes, yes, exactly.
Right. Later you will say what delta phi is in terms of
Yes,
numbers.
yeah. So delta phi is now, I can just perturb.
It's just everything is expressed in terms of delta phi.
Exactly, exactly. Because this makes this.
Works for any.
Yes, exactly.
You can define delta y to be delta 1 plus epsilon.
Yes, exactly. And then, yeah, that's how it. So now we can. Yeah. Yeah.
What is the definition of epsilon? There's some there is some a priori definition of epsilon.
Here?
Define delta phi to be 1 minus epsilon.
So this is the d equals 4 minus epsilon.
The dimension, of course.
Yes. Okay, so I mixed notation. So this should not be that epsilon. This should be something different. So if we plug it in, of getting this function, which is so we get D2s and D2s are there because we are integrating logs. So this is the d bar 1 1 1 1 function that we get in the contract diagram of 4 phi's. So and it comes only from the conformal block of this. So this is the first order correlator.
So why is this effective? Why is that a bulk contact diagram?
I mean, this is just the order epsilon correlator in phi 4 theory.
Yeah, because that precisely captures this double trace exchange. That bulk contact diagram precisely captures the L equals 0 double trace exchange.
Yes.
Pulchinski.
So and you can see that from this expression, this comes out to be automatically crossing symmetric because the way we set it up, it should be crossing symmetric. So this is what we get, and now we need to compute the order 1 correction to this OP coefficient. So we have this expression and we can again decompose it in terms of conformal blocks, and we actually end up getting this OP coefficient. So
your input is that, right? Your input is that delta Z is equal to that and delta L is equal to that, right? Yeah, that's
yes, yeah. So the anomalous dimensions are always input, whatever dimensions we are using. We cannot compute this, the dimensions.
But if I give some other, some other input, I don't know whether theory exists and so on, so I should see inconsistency somehow.
You mean you can try to keep this gamma general?
Use some input which has delta 0 as well as delta 1, let's say.
Okay, so delta 0 and delta 1 and all the higher L's are suppressed. Okay, then you can
calculate something. That's probably your D12.
one thing could be then you can check whether it's crossing symmetric or not.
It will be because as you said, it's bulk contact diagram.
That's because only for L equals 0, but if you are adding something else.
Even for higher L's, Pulchinski and friends tell you that if you have a support, if you have a solution to the crossing equation which only has support over spin 0 and spin L,
Yes.
it can be thought of as a bulk contact diagram. So it's some.
Okay.
What is this? There's some question of UV completion.
Violate the chaos.
So violate the chaos. Because it's large n, right?
Doesn't matter. It'll violate the finite entities.
So unitarity.
Instead of growing like S square, the finite entities it grows like S. It violates the thing that Karen Ho puts in as the assumption to derive this.
So somehow you're saying in some sense the resummation is not going to pull you down.
All I'm saying is that this is what will go wrong, right? You add a check.
Yeah, but the next order etc. will be determined in terms of that and so on. But maybe it,
if you could complete it.
but this is because you a priori know that this works, right?
Yes.
Okay.
Yeah. I think there should be some signature that something is wrong.
I think you'll violate the chaos.
And from here, okay, then one has to calculate the chaos bound.
Yeah, it's basically, Abhijit's asking for, say, next order.
Yes.
Next order, you change some of these L not equal to zeros. Let's say I change one of them. That's like adding one more bulk contactor, which will definitely violate the chaos bound. If I change it at L equals 10.
And it's the same chaos bound is valid in this case.
Yeah, Karen Ho uses chaos bound as an input too.
No, but this kinematic
It's not a
relation
large n context.
No, but even without large.
Finite.
It's just
It's
this-
a finite and
Yeah, it's just this Euclidean thing. The thing that they start the derivation of the chaos bound. Inequality. That will get violent. You know, there's this thing that is true always, and then at large n you approach it.
Yes.
But the thing that should,
But that's small order of epsilon.
you're asking whether it will be violated or epsilon by epsilon. Even epsilon by epsilon, I think.
Maybe it's like a large n.
Yeah, I think so. Because you know, it's just like taking an answer that works and adding something that doesn't work.
Yes, I agree, but if it is like large n, I agree with that. But then one has to think a little bit carefully whether this perturbation epsilon is like the kind of approximation that Malthus and Stanford do, right? Having to do with the
Yeah. We should talk later, but by chaos bound I mean something simpler than what you said. I just mean that Euclidean inequality.
yeah, but that is some all order of epsilon thing.
That is some all order epsilon thing.
So you will never see that, I think. But maybe
I think with this block itself will vary. Then whether that is bad or not, we'll have to argue. We know that block violates.
yeah, but it could resum to nice.
It could be something. Like algebraically, you will see it be violated. Maybe you're saying maybe that's not good enough for that I agree. Okay.
Fine. That's fine.
Okay, so now we have all the data up to order epsilon, and we can keep doing stuff for epsilon for the next order. And at next order you can see that there are all the spinning operators has this anomalous dimension at epsilon square, which is proportional to L, I mean 1 over LL plus 1. So at next order the computation is a bit more involved, and nevertheless one can do this epsilon squared stuff. And order epsilon squared, the
Now you need an infinite number of contributions. Right? You have some,
infinite, yes, yeah,
but you can sum them.
yes, yeah.
That's some. Each is complicated, but the sum is more simple.
Sum is simple here because all the n's are 0,
Because
but
oh, I see.
there is no n, only n equals 0 contributes. So there is only one sum which is from L equals 0 to infinity. But if you go to next order, then all the n's will also come. So it will be a double sum. So it's complicated. So that's why we only have managed to do this up to this order.
Okay.
So this is the second order stuff, and what you all can just write it schematically. So by this I mean the spin 0, and this is the order. And
Even in large n theories, say I want to work up to some particular order in 4-point function, particular order in 1 by n, then if you compute including all the 2-point functions, then you can get 3-point functions of the next order. Even in 1 by n theories.
Same logic.
yeah, so yeah, this is just
So I think that actually even the chaos bound by itself, the derivation will just go through it in epsilon. You know, because chaos bound is a small parameter. Something that suppressed 4-point function compared to product of 2-point functions. Here a coupling constant. There 1 by n did it. Here coupling constant. So at least to some order an epsilon I think is also stored about.
and here at this order you need the derivative of the conformal block. So this is a d-dimensional block, and since we are at next order.
The derivative is needed only for the zeroth pair, right?
Yes, for this order, but if you go to next order, you need for all. So that's why it gets complicated when you move. So this is the 4-dimensional block and the derivatives. And you have all the sum over L. This so this is simple because this is just the 4-dimensional block. We can just do the sum, and since there is only one infinite sum and we know everything, we can do the sum. The complicated part comes from this, but since this is one block, one can manage to do the sum, and we finally end up computing this F2.
Sorry, I don't quite know. I don't quite understand how you do this. L equals to B infinity.
This
Yeah, you know everything, but still there's a big trick that.
yes, yeah. So this is a hypergeometric function.
Yes.
So it will be like something, okay, just some 2 to infinity, it will be some gamma function. Times this k L plus 1 z, where this k is what I defined. Okay, maybe I can, yeah. So this is a hypergeometric function. So this is 2f1 z, and one can actually use the integral representation of hypergeometric function, then do the sum. And since there is only, so
That would be again hypergeometric function or something?
yeah, I can just, no, it will be log square and Li2. So this trick works here at this order, but it fails when we go to next order.
And you can do the integral also of this function?
I mean the discontinuity integral, yes. In some of the integrals Mathematica cannot do, but there is a hyperint which integrates hypergeometric function or logarithmic integrals, but one can try to do it analytically. I didn't try it. Yeah. Sorry. Yeah, but the thing is that this trick works here. So for next order in epsilon, we need to invent some nice way of doing this computation. So that's the only reason we couldn't go to next order. Otherwise, in principle, we should go to. So one is this sum, and the other thing is the derivative of the d-dimensional of the conformal block. So these are the two things. So if one can compute these things, then we know everything. We can.
Also mixing, right? Mixing is not an issue.
Yes, yeah, because here we need the gamma, the dimensions. So you need to, or you need to know the average value. Either you need to know need to solve the mixing problem, or you need to know the average value of this. Yeah, then yes, that's true. So yeah, this is all what I have. Just let me summarize. I can just write it schematically. What are the inputs and output? So we started with the identity operator in a channel and computed the mean field theory correlator, and then it in turn gives the mean field theory operator OP coefficient, and the next order we use this as the input, and also the anomalous dimension that that appear at this order, and the dispersion relation computes this F1, and this will in turn compute A1, and so on. So one can in principle keep going, but yeah. So this is roughly.
But gammas you need to know from somewhere.
Yes, these are always the inputs. Yeah, these we cannot compute using this. Yeah, that's because this enters in the way we are computing the discontinuity, either from Feynman diagrams or from some other bootstrap approach.
The bootstrap approach will give you just some.
Yeah,
Okay, fine.
either from Mellin bootstrap or from
Mellin.
yeah, or from inversion formula one can compute this.
Well, inversion formula will give you large L.
Yes, yeah. For L equals 0, there is this ambiguity. Yeah, yeah. But so these things somehow you have to know a priori. So the thing is that it computes directly the correlator, the closed form expression. We don't need to resum the OP data and compute the 4-point function. So whether it can be extended to next orders in epsilon, that we're currently working on it, it's yet to see. But that's all what I have to say. And I should stop.